Hi everyone. In this video, we are going to solve Educational Codeforces round 190, problem C. In this problem, you are given C1 cards with number 1, C2 cards with number 2, Cn cards with number n, like this. You must take at least 3 cards from the ones you have and arrange them in a circle so that the following condition holds. In every triple of consecutive cards, there are at least 2 equal cards. What is the maximum number of cards you can arrange? So basically the problem is saying that you have some cards of type 1, 2, 3, and so on. This is card of type n. And you have C1 of type 1, C2 of type 2, C3 cards of type 3, and Cn cards of type n, and so on. For example, if you have 1, 1, 1, 3, 4, 4, you have 3 cards of type 1, 0 cards of type 2, 1 card of type 3, and 2 cards of type 4, like this. And what you're told to do, that you have to take some cards from this given cards and rearrange them in a circular manner. So if you want to do like this. Let's say you take all the cards and you can rearrange them like this, or you can take the last these cards and you can rearrange it like this. But the thing is, you always have to rearrange them in a circular manner. Now, condition is you have to take at least 3 cards. So you can take like this 2, 4 and say, okay, this is a circular manner. No, you can do that. And the most important condition is in every triple of consecutive cards, there are at least 2 equal cards. So basically, if you have cards like this, like these are different cards for each 3 consecutive cards, you have to have at least 2 cards equal. So, for example, if this is our combination, then for these 3, at least 2 are equal. At least 2 cards are equal. So these 2 are equal. Here 3 cards are equal. Then for this list, for this triple, these 2 cards are equal. For this triple, these 2 cards are equal. For this triple, these 2 cards are equal. But for this triple, no 2 cards are equal. All the 3 cards are distinct. So you can do that. So basically, this rearrangement is invalid. But let's take an example that 1, 4, 4. This rearrangement is valid. So you're taking 5 cards, this 3 and this 2 cards from the list and rearranging them, and you get a valid rearrangement. Now, what's the maximum? The problem is asking us what is the maximum number of such, what is the maximum number of cards you can fit in the rearrangement? How do we solve it? One thing to notice is that if you have some cards X, let's say you have some cards X, Y, and Z, all of the cards have an occurrence. All of the cards have is more than one time. All of the cards comes more than once in the sequence. So count of X is let's say count of X is 3, Y is 2, and Z is 2. You can actually do this. So X, Y, Z, Z, and you can see that for every triple, no three adjacent elements are. For every triple, we can always find two elements that are equal for every triple. If every element is more than more than one time, we can always do that. So from this observation, we can imply that we can safely do for the cards with which comes more than once, we can rearrange them like that. Like if we have 1, 1, 1, 3, 3, 4, 4, 4, we can always do 3, 3, 4, 4, 4, and okay, sorry, 1, 1, 1, like this. Since each of them actually comes more than once, so they don't conflict with the condition if we place them sequentially. But let's say we have some number. So basically, we can treat them like a valid partition. So we have some x, 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 x. Let's say we have some y, 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 like this. Now, there might be some z or other numbers, like let's say we have a, b, c, d. All of them actually comes once. A comes once, B comes once, C comes once, D comes once. Now, notice that we can't really put them at the end of this sequence or at the beginning of this sequence. So we can put them at the end of any sequence or at the beginning of any sequence. We must put this A in the middle of some sequence. So let's call them actually singular elements. Single elements. Let's denote them as you know, as a dot. now, now, what we can do is that we can count how many singular elements we have. Let's say we have y single elements. So for this list where A, B, C, D are singular, y is like 4. And then we can calculate in this part, in this already rearrangement we built, basically how many single elements this already built rearrangement can fit inside. So if you look at this rearrangement, it can fit one here, can fit one here, it can fit one here, and that's it. We can't actually give it more, because if we do it here, this 3 would be this nothing common. If we put it here, then these 3 are different. If we put it here, then these 3 are different. So wherever we put the single element, there must be some x comes twice on this side, and there must be some y comes more twice or more on the other side as well. It can be that this side has 2 or 3, or this side has 1, because this 3 then elements then become, all 3 becomes different, which violates the condition. So if we have for each sequence of number, let's say x, we have count of x. In this case, count of x is 4. We have to basically the number of single elements we can put inside this sequence is basically count of x divided by 2 minus 1. So in this case, it's 1, because it makes sense that 4 by 2 is basically 2. So if we did only this, so we'd be able to do this. But since we can't do this, we are subtracting along, so this goes. But let's say we have only one element, which is, which occurs more than once. In this case, we can actually, in this case, this, if we straighten this, we can find this line. And in this case, we can actually do this, because in that case, these two, this 3, this part and this part is, this number and this number is the same. So the condition holds true. So we can, here we can just do this, 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 and this, and this. Yeah, we can basically do any of them, but we can't actually, well, can we put one dot here? Let me think. Actually, we can do 1, 2, 3, 4. Yes, we can. It's because, yes, we can. We absolutely can. No, actually we can't, because this might be, this single element and this single element might be different. This might be A, this might be B. So we can't really do that. So yeah, it's not true. So you can only do this. So if we have this, and this, we can actually put one here and put one here. So it's not it's only count x divided by 2, not the minus 1. So we don't need that. So for every x means for every number which comes more than once, we take their count of x and we have our capacity that we can, this is our capacity add. We actually do this. We actually add this number to our capacity. But in the end, if we find one such count which is greater than 1, then we do this. We increment add by 1, since we have place to fit one more single inverse. And finally, what is the answer? Final answer. Final answer is just how many such count x was there, right? For each x, we have count x, because if we have some element which occurs 4 times, we take all of them, and then we have some element which occurs 3 times, we take all of them. So these non-singular elements would be added, and then we add the remaining singular elements. Now, how much do we add? We can add this much, right? Which we calculated like this, but we have at most, we have y single element. So if y is smaller than capacity, then we add y elements, and if the capacity is smaller than what we have, then we add the capacity. So basically, that's the explanation. And let's look at the code. So here we actually calculated our add. So this is the add we calculated for each I. For each element, we actually had their count, and we added them, right? And Cx is basically the elements which have a number of which have occurrence greater than 1, and our initial answer is that sum, that is this part, sum of elements, sum of the count of elements which sum of occurrence of elements which occurs more than once, and then if such element is just one element, one number, if there is such one number whose occurrence is more than 1, then we increment the add, then finally we do this. Finally we do this. And finally, if our answer is less than 3, let's say our answer is less than 3, that means we cannot actually rearrange 3 of them. Then it won't be valid, because it said that you must take at least 3 cards, right? So if our answer is less than 3, then answer is actually 0. So we cannot take at all. So that's our answer. So hope you understood. On the next video, we're going to discuss problem D, which is a TP problem. So until then, bye.